Next, we take a look at some of the concrete examples of how to calculate and interpret confidence intervals for population means. Let's start by looking at a confidence interval that has already been established and see if we can interpret it and find the margin of error. I'll give you a few minutes to think about it before we do it together. For the margin of error, I encourage you to think about how we handled that problem when we looked at proportions. We cannot use the formula to compute the margin of error for this confidence interval since we do not know the values of the standard deviation or the sample size. Rather, we will think about it this way. Each confidence interval is 2 margin of errors wide because it is created by subtracting 1 margin of error from the sample mean to get the lower bound and adding 1 margin of error to the sample mean to get the upper bound. 1 plus 1 is 2. So once again, we see that every confidence interval is 2 margin of errors wide. So we choose to calculate the width of the interval. We could choose to calculate the margin of error by taking the width of the interval and dividing it by 2. So the interpretation would go like this. With 90% confidence, we can state that the average teacher's salary is between, if you think back to the previous slide, is between $38,944 and $42,893. Those were the boundary values. It's very important to use the word average or mean here. This is definitely not a statement about an individual teacher in Nevada, but rather about the average salary of all teachers in Nevada. The margin of error is found by calculating the width of the interval and dividing by 2 as described in the previous slide, and it is 1,974. We interpret this as, with 90% confidence, we are able to estimate the average teacher's salary in Nevada accurate within $1,974.50. To increase our confidence level to 95, the price would be that we would have to pay is the margin of error would be larger, and the confidence interval would be larger and less precise. For our next example, we would like to estimate the true mean body temperature of healthy adults. I've always been told it's 98.6, but is that accurate, and could we collect some data to see if it is? So we will look at 52 subjects, adult subjects, that reported a mean body temperature of 98.285 with a standard deviation of 0.6824. So let's compute both the 95 and the 99% confidence interval for the average body temperature of healthy adults. The first step is to use the online t-calculator to determine the appropriate critical t-value. We have 52 subjects and hence 51 degrees of freedom. The confidence level is 95%, so the area between will be 0.95, and we'll make sure the between is checked off. The calculator reports back a value of 2.088. Next, we calculate the margin of error, which is the t-value, 2.088, times the standard deviation, 0.6824, divided by the square root of the sample size, which is 52. So the margin of error cooks up to be 0.19, which gets added and subtracted from the sample mean. And we can conclude that with 95% confidence that the true average body temperature of healthy adults is between 98.095 and 98.475. The calculation of the 99% interval is very similar. The only difference will be in the critical value of t. Now the area in between becomes 0.99. We get a new critical value. This should say 76. And the margin of error cooks up to be 0.249, which is larger because we've increased the confidence level. This makes the confidence interval wider. When we subtract and add the margin of error, we get boundary values of 98.036 and 98.534. So this slide puts together both confidence intervals in one place. I remind you of the summary stats, the 95% interval and the 99% interval. We will note that the 99% interval is somewhat wider. Both contain the value 98.6, so there seems to be in fact, actually, both of them are less than 98.6. So there seems to be an indication that the mean adult body temperature of healthy adults is actually less than 98.6. For our last example, a certain company wants to compare the calorie content of strawberry and vanilla yogurt. I have stored this data in a file called yogurt.xls. It's an Excel file on my computer. Let's see what happens when we load that into StatCrunch. So let's look at the data. It consists of the calorie content of 11 brands of yogurt, both strawberry and vanilla. So I'm going to select T-Stats, one sample. When it comes to selecting the columns, I'll select both strawberry and vanilla. So then what we're going to do is we're going to select confidence interval, not hypothesis testing, and make sure the confidence level is set at 0.95. So the upper and lower boundary values for both strawberry and vanilla are given. The 95% confidence intervals can be expressed as we are 95% confident that for strawberry yogurt, the average calorie content is between 142.7 and 200.6 calories, whereas for vanilla, the average calorie content is between 128.8 and 189.5. I drew a little visual, And we see that the 95% confidence intervals overlap, so that we cannot be 95% confident of a difference in caloric content of strawberry and vanilla yogurt.